So in this video we're going to talk about the average power delivered by the components. Now remember we had two ways of computing this, and I'm not talking about whether we have effective or R versus non-effective. We have our equation here that my average power is 1/2 Vm Im cosine of theta v minus theta I. But then we also, at the end of the previous video, said that another way we could do this is looking at 1/2 the real part of the phasor voltage times the complex conjugate of the phasor current. So we're going to use this first here to examine what the average power is delivered by a component. So for a resistor, this one actually turns out to be relatively easy. A resistor here, theta v equals theta I. Now of course this is in the ideal case, but even if you go into a lab or you could just even go into your own lab, put a resistor in your breadboard, hook up your function generator to it, measure the input and measure across the function generator and then measure what's on the output across that resistor, and you're going to basically get the same thing. So and so if this is no phase shift here, then we can get simply that the power is going to be 1/2 Vm Im times the cosine of 0 degrees. But cosine of 0 degrees is simply just 1. So for a resistor, power actually just boils down to 1/2 Vm Im, which we could rewrite as 1/2 Im squared R, or 1/2 Vm squared divided by R. Now, I'll put it off to the side here. Remember, if you're given effective values, this would just be essentially V effective times I effective, which would be I effective squared times resistance, or V effective squared divided by the resistance. So that's what average power is for a resistor. For a capacitor and inductor, it turns out that the average power for a capacitor is equal to the average power for an inductor, L for inductor, which is equal to 0. Now, you don't want to think that a capacitor and inductor have no power or energy stored in things like that. That's not the way you want to think about it. It's just that it's not average power. It turns out this is going to be something that's called reactive power. And this actually, we're going to notice later on in the discussion of power, is going to become quite important, because while reactive power is real in the sense that it's there, it's not imaginary, I mean it's there, reactive power is absolutely present in a circuit, it's not something we can use to turn the crank. And we're also going to be wanting to make sure that we deliver maximum average power, for instance, to a load. And one thing we're going to have to do to try and do that is, quote, cancel out the reactive components. So it's going to become important, but as far as average power goes, the power to actually be able to turn a crank, the capacitor and inductor don't have any average power. Now again, this is for AC circuits, not DC. Okay, now we could go through the math on why this is the case, but I think the easiest way is just to go through a simple example to illustrate this. So I'm going to give us a power supply of J10 volts, a resistor of 6 ohms, and a capacitor of minus J8 ohms. And we're going to compute the average power through each of the things, but we're going to use this formula here, that this is equal to 1/2 the real part of VM times, not VM, we're talking about phasors here, phasor voltage times phasor current conjugate. And the reason we're going to do that is that's honestly when we were doing all of our analysis in the previous chapter, we were doing things and we had everything in phasor form. So since we're already doing circuit analysis in phasor form, it might make sense just to go ahead and use the formula that already deals with phasors. Okay, so let's go ahead and do this. Well, what I'm going to do here is I'm just going to simply compute this phasor current I, because then I can use that phasor current to compute the phasor voltages of each of these terms and use that to compute the average power. So the phasor current, hopefully this is all pretty obvious for you, because this is a simple series circuit. It's just going to be J10 divided by the sum of the impedances, 6 minus J8, which if we do this, I have this on my calculator right here, I did this computation. We get negative 0.8 plus J0.6 amps. Now, if I do this here, I'm going to first calculate the voltage across the resistor. So that's just simply voltage times, current times resistance. So that would be negative 0.8 plus J0.6 times 6 ohms, which gets me negative 4.8 plus J 3.6 volts. And now I'm going to go ahead and compute the power, and this is 1/2 the real part of the voltage, which my voltage is minus 4.8 plus J 3.6. Now it's the conjugate of the current, so it's minus 0.8 minus J0.6 because I got to do the conjugate of the current. And if I do that, I get 1/2 the real part of 6. Now you might say, well, what's the real part of 6? Well, don't overthink this. The real part of 6 is just 6, because 6 is equal to 6 plus J0. So the real part is just 6. So my answer here is that the average power that the resistor is absorbing is 3 watts. Now let's do the same thing for the capacitor. Voltage across the capacitor, same idea, minus 0.6 plus J0.6 times the impedance, which is minus J8. And if I do that computation, I get 4.8 plus J6.4. And then if I try and compute the average power, I get 1/2 the real part of my voltage, 4.8 plus J6.4, times my current conjugate, negative 0.8 minus J0.6. And if I do that, I get 1/2 the real part of minus J8. Which again, don't let the minus J8 confuse you. That would be minus J8 is simply 0 minus J8. So the real part, which is sitting right here, is 0. So this would be 1/2 times 0, which is, of course, 0 watts. So it's absorbing no average power. Now this is where the reactive power is going to come in though, because notice I didn't get 0 as my answer here, when I did the voltage times the complex conjugate of the current, I got an answer. It was just imaginary. And remember, we want to think of imaginary as not being real, as being a different mathematical tool for us to answer questions. So there's a question that was answered here. The question that was answered is we need to figure out, what does this mean? And it turns out this is going to be the reactive power that is on the capacitor. So I'm going to end the video here. The next video I'm going to do one more example of computing average power, and then we'll move into the reactive power.